Hey everyone, and welcome. We're about to go on a little journey to understand something we use every single day, but, well, we rarely stop to actually think about it. Numbers. And you're going to see the story of how we got them is this incredible tale of solving one problem at a time. I mean, really, stop and think for a second. Where did they even come from? And why do we need so many different kinds of them? It turns out our number system wasn't just discovered all at once. Nope, it was built piece by piece, layer by layer. And each new type of number was invented to fix a problem that the old numbers just couldn't solve. And this right here, this is the core idea for our entire journey today. We're going to start with the simplest, most basic numbers and then just build our way out. You'll see how each new set of numbers was created to answer a new kind of question, wrapping around the last set and basically expanding what we could even do with math. Okay, so let's get into it. Part 1, Beyond Counting Numbers. Our story starts with the very first numbers humanity ever needed and the surprisingly simple problems that forced us to invent something totally new. Pretty simple question, right? You've got 7 apples, you need 12. How many more do you need? To answer this kind of problem, you only need the first, most intuitive set of numbers humans ever came up with. And here they are, the natural numbers. 1, 2, 3, the counting numbers. They're beautifully simple. If you add 2 of them, you get another one. Same thing if you multiply them. In math, we say the set is closed under those operations, which is really just a fancy way of saying you can't escape the set. Everything just works perfectly. Or, well, almost perfectly. And boom, just like that, our simple little system hits a wall. The answer, x equals 0, it doesn't exist in the natural numbers. Think about it, you can't count to 0. So to solve this, we had to invent a brand new number. So we invent 0. And inventing 0 immediately unlocks its opposite, negative numbers. And together, they give us the integers. Now this was a huge breakthrough. It meant that for any number, there was another number that would cancel it out perfectly, right back to 0. This is what finally made subtraction work for any 2 numbers you could possibly think of. But you know how this goes. As soon as we solve one problem, another one pops up. You try to solve this equation, you get x equals -9/7. And that's not a natural number. It's not a whole number. It's not an integer. We've hit another wall. We need another layer. Which brings us to section 2, the rational universe. The next invention was so powerful, so seemingly complete, that for centuries, mathematicians were convinced they had found it. The final form of numbers, a perfect system that could describe, well, everything. These are the rational numbers. The name comes from ratio. It's any number that you can write as a fraction, a ratio of 2 integers. In this set, it includes everything we had before, right? Because any whole number, like 5, can just be written as 5/1. And this system is incredibly robust. I mean, look at this. Addition, subtraction, multiplication, they're all closed. You always get another rational number back. You can even divide by any rational number, as long as it's not 0, and you stay inside the system. It's a self-contained universe, what mathematicians call a field, where all the basic rules of arithmetic just work. And not only that, they are dense. Now, what does that mean? It means that between any 2 rational numbers, it doesn't matter how ridiculously close they are, you can always find another one, and another, on and on into infinity. This created this powerful illusion that the rational numbers filled up the entire number line completely with absolutely no gaps. For hundreds of years, this was just the truth. The rational numbers were everything. And then a discovery was made that was so shocking, so world-shattering, that legend says the guy who found it was thrown overboard and drowned to keep it a secret. I mean, it makes sense. With this dense, perfect system, there couldn't possibly be any gaps left on the number line, right? Yeah, about that. They were completely and utterly wrong. The ancient Greeks themselves found a number that shattered their entire perfect system. The whole crisis came from the simplest shape you can imagine. Take a square with sides that are exactly 1 unit long. How long is the diagonal? Well, Pythagoras tells us it's the square root of 2. But the Greeks proved that this number, this physical length that you can literally see and measure, cannot be written as a fraction. It was a hole in their number line, a totally new kind of number. So this gives us our great divide. On one side, you have the rational numbers. As decimals, they either stop or they fall into a nice, neat repeating pattern. On the other side, The irrational numbers, like the square root of 2 or pi. Their decimal expansions go on forever, and they never ever repeat. They're just chaotic. And the number line was riddled with these irrational holes. All right, section 3, completing the number line. So how do you fix a leaky number line? You can't just find all the holes one by one and plug them up. You need a new fundamental rule, an axiom that just guarantees there are no holes to begin with. And this brings us to our final layer, the real numbers. Now stick with me, because this sounds a little abstract, but this is the magic ingredient, the least upper bound property. It is a formal guarantee that the number line is a true, unbroken continuum. All it says is that for any group of numbers that has some kind of ceiling, there has to be a lowest possible ceiling. And this is how it brilliantly plugs the hole for the square root of 2. Just imagine all the rational numbers that, when you square them, are less than 2. You know, numbers like 1.4 or 1.41. This collection of numbers has plenty of ceilings, right? 1.5 is a ceiling, 2 is a ceiling. But what's the absolute lowest ceiling you could possibly have? The least upper bound property just guarantees that one exists. And that number, that lowest possible ceiling, is precisely what we define as the square root of 2. It plugs the hole perfectly. Okay, last section. Why real numbers matter. So we've been on this long, pretty abstract journey to build a complete, gapless number line. But this isn't just some mathematical game. Why does having this full set of real numbers actually matter in the real world? Well, because that gap we found, the square root of 2, it's just the tip of the iceberg. The real world is overflowing with these irrational numbers. Without pi, you can forget about modern engineering or physics. Without the number e, modern finance and economics just fall apart. Even a simple sheet of A4 paper has its proportions defined by the square root of 2. Completing the number line is what allows our math to actually describe the world we live in. So we've come a long way, from just counting on our fingers to building this complete, continuous line of real numbers. We built a system that could handle adding, subtracting, multiplying, dividing, even finding roots of positive numbers. But if this journey has taught us one thing, it's that every solution seems to reveal a brand new problem. So what happens when you ask this question? What's the square root of -1? Well, that's a story for another explainer. Thanks for watching.